Hello everyone, I'm James. One moment. Hello everyone, I'm James and welcome to episode 4 of the OpenGL tutorial series. Today we're finally covering the topic of shaders. To understand the purpose of shaders, we need to take a look at our scene. There is a lot to be desired. Our scene is very static and doesn't look 3D at all. How can we transform the vertices to make this scene a little bit more interesting? This is where the vertex shader comes in. The vertex shader is a program that transforms every single vertex in our mesh. In our case, our mesh only consists of 3 vertices, which make up one triangle. The vertex shader takes one input. This input is the vertex we're currently working on. Then it outputs a position, the position we actually want on the screen.
This is an example of a very simple vertex shader. In fact, if we had to use this vertex shader for our program, we would get the exact same result. The language of the shader is called GLSL, which stands for Graphics Library Shading Language. There are many versions of GLSL. That is why we have to specify the version at the top. The version I chose is 330, which means 3.3. This version will be good enough for our purposes. This line specifies what kind of input vertex the shader is expecting. It is also called an attribute in other versions of GLSL. When our vertices will have more components apart from the position, we'll have more of these attributes. This is the main function, where we can do all the fancy stuff to transform our vertex. In this case, nothing fancy is happening. All we're doing is converting the input vertex into a 4-dimensional vector and assigning it to GL position. GL position is not simply a variable, it is the output position of the shader that we mentioned earlier. The output variable's type is a 4-dimensional vector, which is why the conversion is necessary. What can we do to make this shader more useful? What we can do is add another input, apart from the vertex, and this input will be a transformation matrix. How can we add this input? This is where uniforms come in. Uniforms are the bridge between our C++ source code and the shader source code. We can add a uniform with the uniform keyword and specify the type of the uniform. In this case, the type is mat4, which is a 4x4 matrix. We can now transform the vertex position by multiplying the matrix with it.
You might wonder, why is GL position a 4-dimensional vector? And why do we use a 4x4 matrix to do transformations? I think the reason why we have to do that is outside of the scope of this series. There are other good tutorials that can explain that better than I can, so I'll leave a link about that in the description. There's another thing really ugly about our scene. The scene has no color, no textures, nothing. It's just a white triangle and a black background. Actually a purple background because I made it purple. But our triangle is completely white. What can we do to make it more interesting? This is where the fragment shader comes in. Unlike the vertex shader, the fragment shader runs on every single pixel that is rendered to the screen. And since we can control every single pixel, we can, for example, make all the pixels red or all the pixels purple. Ideally, we don't make them purple because our background is purple and the triangle won't appear at all.
This is an example of a fragment shader. We need to specify the version just like the vertex shader. The output of the fragment shader is also a 4-dimensional vector, its components representing the red, green, blue and alpha channel. This shader is also doing nothing special, it's simply outputting a white color. Uniforms are also accessible in the fragment shader. We can, for example, add a color uniform and output that instead.
Now it's time to create these shaders, load them up and start playing with them. Writing the shaders is the easy part. The hard part is compiling the shaders and checking for errors. There are a bunch of functions we need to call, and I'll be explaining every function in the best way possible I can. However, if you still don't understand, there's always the OpenGL documentation that you can take a look at, and there will be details about every function and what every parameter does. Let's go ahead and get started.
I created a header and source file called shader. I also went ahead and created a shader class in the header file. I'll begin by adding a constructor, which is going to take in the source code of the vertex shader and the source code of the fragment shader. We'll need to import string. There is this concept in OpenGL where a program is a group of shaders. We're going to add a field for the ID of that program, and we'll need to import glue. There are a few more things I want to add to the header. First, a destructor, which we'll implement in the source file. Secondly, a bind method. This will tell OpenGL to use the current program. I'll also add 4 private helper methods. 2 of these methods will be responsible for checking errors. The first method will check errors for our program. This will take in the kind of error we are checking for and what message we want to print, if an error is indeed found. The other method will check for errors in a single shader. This will take in the same parameters as the function above, however with an additional parameter for the shader ID. I want 2 other helper methods. The first one is going to compile the program. This won't take any parameters. The second one is going to add a shader to our program. This will take 2 parameters. The first parameter is a string representing the shader's source code. The second parameter is the kind of shader, in our case a vertex or fragment shader. I almost forgot to add this field. This field will keep track of all the shaders we have created. Make sure you include vector. Now in the shader constructor, the first thing we need to do is create a program by calling glCreateProgram, and I'll store its result in the program ID field. Next I'll call the add shader twice, first for the vertex shader and then for the fragment shader. All that is left to do in the constructor is compiling the shader. Now let us implement the shader destructor. The reason why I kept track of the shaders is so that I can destroy them properly. All we have to do is loop through the shader IDs and call glDeleteShader on each shader. Finally, we'll delete the program. Now let's implement the addShader method. First we'll create the shader, passing in the type for the type. And we'll store the result in a variable. Next we'll check if the ID is 0. If it is, that means that OpenGL didn't find enough space in memory to allocate for this shader. Make sure you import IOStream. Now we need to set the source code of the shader by calling glShaderSource. The first parameter this takes in is the shader ID. The next 3 parameters are slightly weird. The second parameter is the count of source codes, in our case 1. The third parameter is a pointer to an array of pointers to characters. In our case we're only going to have 1 character array. So I'll create an array of pointers to characters containing 1 pointer to our source code. The final parameter is an array of the lengths of the previous parameter. I'll make an array of glint containing just 1 length, which is the length of the source code. With that, we can now finally compile the shader. Next we'll check if the compilation failed. Now we attach the shader and finally add the shader ID to the list of shaders. Now let's implement the compile method. This should be a lot simpler. First thing we'll do is link the program. We'll check for errors right after. Next we'll validate the program and check for errors right after as well. Now we'll implement the checkProgramError method. The first thing we'll need is a storage for the error result and the storage for the error message info. I hard-coded 104 characters for the message, which probably isn't a great idea, but this should be good enough for our purposes. Next we'll call glGetProgramIV, which will give us error info. The first parameter is the program ID, the second parameter is the error type, and the last parameter is a pointer to an integer variable where the status is going to be stored. If the status is equal to GL false, Then we get the error info and print it. The check shader error is so similar that I'm going to copy and paste. The only thing we need to change is to call getShaderIV and getShaderInfoLog while passing shader instead of program ID. Implementing the bind method is very easy. All we need to do is call GLUseProgram, passing in the program ID. I added a load function in the shader class which loads a shader. The code will be available on GitHub.
The way I wrote the load method in the shader is by loading it from this path, so from the program spot ./res/shaders. And that's what I did. I made a folder, res in the project folder, shaders, and there I put my shaders. Then I loaded the shaders simply by their name here, and then I bound the shader. So let's take a look at the shaders. We have the vertex shader, the fragment shader and the vertex shader. The vertex shader is very simple, it just outputs the position, and the fragment shader is also very simple, but it outputs the color red. Let's see what happens if we run now. Look at that, we get a red triangle. That means that our shaders are working.
There is another concept in shaders that I want to show you. In the vertex shader, we can define another output variable, which is called a varying variable in older versions of GLSL. A varying variable is the bridge between the vertex shader and the fragment shader. To declare a varying variable, we need to declare the variable outside of the main function with the out keyword. I'll be sending out the vertex position. So in the main function, I'll set the varying variable to the vertex position. Inside the fragment shader, we need to take in the varying variable, and we do that with the in keyword. Instead of outputting red, let us output the vertex position.
If we run right now, we get this result. Pretty interesting, isn't it? So what is happening here? Well, we're outputting the position as the color. The position is made of 3 components, X, Y, and Z. Colors are made of 4 components, R, G, B, and alpha. However, we're ignoring alpha for now. And in fact, if you look at it, you can see that when the X is increasing, red is increasing. And when the Y is increasing, the green is increasing. This black area is caused because the position is between -1 and +1 for both axes, and colors are between 0 and 1. What can we do to remove this? Well, in the shader, we can multiply, in the vertex shader, we can multiply the position by 0.5 and add 0.5. So if we run now, we get this. Look at this, it's so interesting. So now we're getting the ranges from 0 to 1 for red and from 0 to 1 for green. But you might see that there's some blue in here. And the reason for that is that all these vertices, the Z value is 0. And our calculation grabs the 0, multiplies it by 0.5 and adds 0.5. So the result is 0.5. So we have some blue, we have 0.5 blue at every vertex. So yeah, pretty cool.
And that, my friends, is the end of this video. In the next video, we are going to add the transformation framework. That way we can rotate or scale or move the triangle in 3D space. If you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell. With that, thanks a lot for watching and goodbye.